So in this third part of the video, we're going to take a look at the stringer method. What this stringer method is going to allow us to do is to use a bit of research, a research finding, to calculate stroke volume when we do a graded exercise test and we know oxygen consumption, we know heart rate, and we can determine a VO2 difference based on the percentage of VO2 at which we're calculating stroke volume. So how do we go about this? Well, I want to describe the stringer method in a little bit more detail first. What they did was measured 5 healthy volunteers, and each one of those volunteers did 2 graded exercise tests. So they had a total of 10 tests. Now what they did with that information was formed a regression equation. Using a metabolic cart, they measured oxygen consumption. Using a heart rate monitor, they measured heart rate. Now they were able to also determine stroke volume, so they measured this. And then VO2 difference again was measured. Once they knew all the variables in the equation, they could figure out a formula that allows you to calculate this based on regression analysis. So that looks like this. And what we can see with the regression equation is that you get a line of best fit in an equation. So they determined that in order to figure out a VO2 difference without having to put a catheter into your artery, into your vein, and then measure the difference, you could estimate it with an equation that's 5.72. Okay. The units here are mils of O2 per 100 mils of blood. Come back to that. Okay, plus 0.1 times the percentage of VO2 max. So what this works out to is that after you've completed a graded exercise test, you start at a 0 intensity, you finish at 100% intensity, you've gone through your criteria and you've achieved VO2 max, I can look backwards into that test and determine at some point earlier on what percentage of VO2 max I was working. At the end of the test, you're at 100% VO2 max. At the start, you're at 0. For example, here, if your VO2 max is 5 liters, when you're at 2.5 liters of oxygen consumption, 2.5 divided by 5 is equal to 0.5, which is 50%. So if we're going to use that point of the test with with the stringer method, this number would be 100%. So let's just do that now. Okay, this simplifies to 10. 100 times 0.1 is 10. And we're left with an answer of 5.72 plus 10, which is equal to 15.7 mils of oxygen per 100 mils of blood. So how is this helpful? Well, let's assume we've done a graded exercise test. We know that at VO2 max, so that means we've achieved at least 3 criteria, that our oxygen consumption is 4.527 liters of oxygen per minute. And we know that at a VO2, when our RAR was equal to 1.0, so there and abouts the anaerobic threshold, our oxygen consumption was only 3.305 liters of oxygen per minute. And we know that at that same time point, around the anaerobic threshold, our heart rate was equal to 150 beats per minute. Well, we can see that we're able now to fill in a lot of these variables. Our oxygen consumption, our heart rate, we don't know the stroke volume, and we don't know the VO2 difference, but we can use the stringer method to fill in this blank and then we can calculate stroke volume. So this is what we're going to do for this example. First of all, let's convert VO2 max into milliliters of oxygen. So 4.527, if we needed to get into milliliters, becomes 4,527 milliliters of oxygen per minute. And again, at that point earlier in the test, 3.3 becomes 3,305 milliliters of oxygen per minute. And then we need to determine what percentage VO2 is 3,305 mils. So we do a little equation here. 3,305 divided by 4,527 times 100 will give us a percentage of VO2 peak, because 4,527 was oxygen consumption at VO2 max. We'll find that equals 73%. Now we can take this number and insert it into the Stringer method. So A minus VO2 difference is equal to 5.72 plus 0.1 times 73%. Okay, do the math, and the number we get is 13.02 milliliters of oxygen per 100 milliliters of blood. Now, the next step is not terribly difficult. We're going to rearrange the Fick formula to solve for stroke volume. There's a trick here though, which is to account for this 100 mils of blood. So the units involved have to all cancel out appropriately to determine how many milliliters of blood leave the heart. So how do we do that? Okay. We solve for stroke volume. Stroke volume, according to the Fick equation, okay, if we rearrange to solve for it, is going to equal to VO2 divided by heart rate and AVO2 difference but we also have to move this to the top and multiply by 100 mils of blood. Okay, let's put some units in, it'll make more sense. So if we use our information thus far, stroke volume is going to equal to 3,305 milliliters of oxygen times 100 milliliters of blood divided by the heart rate of 150 beats per minute times the AVO2 difference of 13.02 milliliters O2. Now again, we've taken that 100 mils of blood and we've moved it to the top of the equation so the units will cancel. So minutes cancel. Let's do this in a different color. Minutes cancel. Mils of O2 cancel. And we're left with blood. And we're left with beats. So when we get our answer, so 3,305 times 100 divided by 150 times 13.02, stroke volume is equal to 169.23 milliliters of blood per beat. Let's just circle that. The last thing we can do is calculate cardiac output. So Q, cardiac output, is equal to heart rate times stroke volume. there's our stroke volume, and there's our heart rate. So Q is equal to 150, okay, beats per minute, times 169.23 mils of blood per beat. And we're left with an answer, it's going to be a large number here, 25,384 milliliters. Or, if you want that in liters, we divide by 1,000, we get 25.384 liters per minute. So that's cardiac output. That's stroke volume. Okay. And up here we calculated we estimated a VO2 difference. And the Stringer's research allowed us to do all those things. The last thing I'd like to do to put that in perspective is to show you what 150 mils of water looks like. So as you can see here, that's 150 mils of water. Okay? So it's important when you get your final answer, ask yourself, does it make sense? Okay? If my heart is the size of 2 fists, can it contain 169 mils of water or blood? Yes. Okay? Can it contain 1,692 milliliters or a liter? No, it can't. So always take a look to make sure that you multiply it appropriately and that your units make sense.